right, today we're putting on our engineering hats and heading straight to the workshop. We're going to walk through a real 6-step process for taking all that raw data from a machine, the vibrations, the temperature, and actually turning it into an intelligent system that can see a failure coming. So this isn't some high-level theory. Nope, this is a practical, hands-on blueprint for building a machine learning model right from scratch.
Think about it for a second. Every single motor, every pump, every gearbox on the factory floor, they're all constantly telling you a story. They're talking through their vibrations, their temperature changes, their sounds. So the big question is, are we actually listening? Can we take that physical language and translate it into digital intelligence? Well, that is exactly what we're going to dive into today.
So, our whole mission here is to figure out how we go from all that raw, chaotic noise coming off the sensors to something clean, something useful, something we can act on. It's really about taking the messy vibrations from, say, a spinning bearing and using them to predict exactly when it's going to need maintenance. I mean, we're talking about saving time, saving a ton of money, and maybe even preventing a catastrophic failure.
And here's our roadmap for today. We've got 6 key steps. We'll start with defining our mission and go all the way to deploying a working solution on a real machine. This is basically our game plan for building a truly smart system from the ground up.
Okay, first things first. Before we even think about collecting a single piece of data, we've got to know exactly what question we're trying to answer. Having a crystal clear mission is the bedrock of any good engineering project, and believe me, machine learning is no different.
So, what kind of mission are we talking about? Well, are we trying to classify something? Like, is this pump's condition normal, cavitating, or blocked? We're just putting it into a category. Or maybe we're doing regression. That's where we predict a specific number, like how many hours exactly does this bearing have left before it fails? That's a huge one. Or we could be doing clustering, where we let the data group itself to find a turbine's hidden operating modes. The point is, the type of question we ask right now, that sets the stage for everything else we're going to do.
Okay, mission defined. Now it's time to roll up our sleeves and get our hands dirty. I love this part, because it's kind of like being a digital blacksmith. We take this raw, impure metal, which is our sensor data, and we start hammering and shaping it into something strong, refined, and actually useful. And where does this raw material come from? Well, from a whole toolbox of sensors. We're talking about things like accelerometers bolted right onto a motor to measure every little vibration, or temperature sensors tracking the heat on a turbine. We might even use thermal cameras to look for hotspots. Each one of these gives us a unique piece of the puzzle. But here's the thing, and this is super important. The data you get straight from these sensors, it's messy. It's full of electrical noise, background chatter, all kinds of junk. And if you try to feed that raw signal straight into a model, well, you know the saying, garbage in, garbage out. It absolutely has to be cleaned up first. And this is how we do that refining. First up, we filter the signal, just to strip out all that electrical noise. Next, and this is probably the most crucial part, is feature extraction. See, we're not just dumping raw waveforms into the model. No way. We're calculating smart metrics, things like root mean square, which tells you the overall energy of the vibration, or kurtosis, which is amazing at detecting those sharp, spiky impacts, a classic telltale sign of a bearing fault. Then finally, we normalize everything, basically squishing all our data into a common 0 to 1 range. This just makes sure that one big measurement doesn't drown out all the others.
All right, our data's clean, it's forged, it's ready. Now we have to pick the right tool for the job. And it's just like in the workshop, right? You wouldn't use a sledgehammer to turn a tiny screw. Same idea here. You just can't use a regression model for a classification problem.
And this choice, it goes straight back to the mission we set in step 1. So if our mission is classification, like figuring out a specific fault in a gearbox, a decision tree is a fantastic place to start. But if we're predicting CNC tool wear, that's a regression problem. We might reach for something like a support vector regressor. It's just really good at finding that best fit line through complex data. You see how the mission we defined at the very beginning dictates the tools we use now?
Okay, we've got our data, we've got our tool. Now it's time for the magic to happen. We're going to train our digital brain. This is the phase where the model actually learns to connect the dots, to see the patterns that link our sensor data to the real-world outcomes we care about, like an imminent bearing failure.
Now, to do this right, we have to split up our data. Think of it like this. We give the model about 70% of the data to study from. This is its training data. It pores over this stuff to learn all the patterns. But we keep the other 30% hidden. That's the testing data.
It's like the final exam. We use this data the model has never seen before to make sure it actually learned the concepts and didn't just memorize the answers.
Now, as engineers, we don't always have massive data sets to work with, right? And that's where a technique called k-fold cross-validation becomes super handy. Instead of just one big final exam, imagine we give it a bunch of smaller pop quizzes. We split the data into, say, 5 chunks, then we train the model 5 separate times, each time using a different chunk as the quiz. This just gives us a much more trustworthy and robust score of how our model will actually perform out in the real world.
So, we've trained a model? Great. But is it any good? How do we know? This is where we have to put on our judge's hat, because a model is completely useless if we can't objectively measure how well it works. This isn't about gut feelings, it's all about the hard numbers.
And for a classification model, the absolute best tool for the job is something called a confusion matrix. It sounds complicated, but it just breaks down every single prediction. A true positive? Awesome. That means we correctly spotted a fault. But check out the false negative. That's the dangerous one. That's a fault we completely missed, which could lead to a catastrophic failure. And then you have the false positive. That's a false alarm, which means costly, unnecessary downtime. We need to understand the trade-offs here.
This brings us to a really key metric called recall. Forget the formula for a sec. What it really means is, of all the actual faults that happened, what percentage did our model actually catch? That's it. And if you're a maintenance engineer, recall is probably your #1 metric. Why? Because you'd much rather deal with a few false alarms than miss a single real failure that's about to happen.
Now, the other side of that coin is precision. This asks a different question. When our model does raise an alarm, how often is it right? In other words, when that alarm goes off, can we trust it? High precision is what saves you from those costly, unnecessary shutdowns. And the real art of engineering here is finding that perfect balance between high recall and high precision for your specific machine.
Okay, we've built the model, we've trained it, we've graded its performance. Now, for what I think is the most exciting part, taking it off our laptop and putting it to work on the actual machine out there in the real world.
But just before we let it loose, there's one last step: hyperparameter tuning. The best way to think about this is like fine-tuning an engine. We're just tweaking all the internal knobs and dials of the model to squeeze out every last drop of performance, making sure we get the best possible recall or precision.
And this is what it all comes down to. This is the whole system in action. You've got live data streaming from the sensors. It flows into our model, which is running on a tiny little computer right there on the shop floor. The model makes its prediction in real time, and if it spots trouble, bam, an automated maintenance alert goes out. This right here is the payoff for everything we've done.
So let's just boil this entire process down, shall we? We start with messy data. We pre-process it into something clean. We feed that to a model. The model makes a prediction, and that prediction leads to smarter maintenance. That's the whole workflow in a nutshell.
And that really gets to the heart of it, doesn't it? This whole process, it's not just about adding another fancy tool to our engineering toolbox. It's about a fundamental shift in how we design, run, and maintain machines. The next big leap forward isn't just about inventing stronger materials. It's about building machines that are smarter, that are self-aware. So the real question is, what are you going to teach your machines to do?